I just want to add a couple of things that didn't make it in the regular lecture. So a complex number, like we discussed, has this form, and it can be depicted in the complex plane like this, right? So it's kind of like a vector. What if you add two complex numbers, right? So if I have C1 equals A1 plus I B1 and C2 equals A2 plus I B2, well, that's equivalent to basically doing this. So you have complex number one that has components A1 and B1, and then you add to it complex number two, right? So this right here is A2, and well, maybe this is not a very good drawing. So let's say it was something like, yeah, like that, right? So this is A2, and this right here is B2. And so then the net, the sum is this complex number right here. You see, so this is the sum. This is C1 plus C2. And so if you have two complex numbers, it's very useful to think of adding them graphically in this sense. Again, it's just like adding vectors. And so you can make several conclusions about the range of the outcome of the sum, what can possibly happen. So if I have two complex numbers that have different magnitude, you can see that the two extremes are their phases are the same, right? So they have the same phases. So this is phi 2 and this is phi 1. The phases of the two complex numbers are the same. And so then by adding complex numbers with magnitude C1 and magnitude C2, the largest possible magnitude is C1 plus C2. And vice versa, another extreme that could happen is if phi 1 and phi 2 are pi apart. So this is phi 1 and this is phi 2. And I just have to kind of just shift the second one a little bit so you can see. So this is, you see, this is phi 1 and this is phi 2 equals phi 1 plus pi. Okay, it's turned. And so then this says that if you have two complex numbers with magnitude C1 and C2, then the smallest possible magnitude, which would happen if phases are related like that, is this one. It's this or C2 minus C1, depending on which one is big. If C1 is bigger than C2, and it's the second if C2 is bigger than C1. So this graphical thinking in terms of aligning these numbers in complex plane, just like you would align vectors, it's helpful for us to realize the range of possibilities. If I have, say, many complex numbers, let me pause this for a second. Before I talk about many complex numbers, let me give you another example. Let's say I have C1 and C2. Okay, so this is the net sum. But what if C2 had a different phase, right? So what if C2 had a, what if C1 was like that, but C2, I want to make sure C1 is the same, like, but C2 was oriented differently. It had a different phase. So you can see that the sum will have a smaller magnitude, right? C1 plus C2, C1 plus C2, okay? And so depending on the phases, the outcome can be a complex number with magnitude given by this, or so that's the outcome with the largest possible magnitude, or it can be outcome with the smallest possible magnitude given by this, or by this, depending on which of the two numbers, C1 or C2, has the largest magnitude. And if I have many complex numbers, so let's say I have, say, 10 complex numbers, so I add them like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see, the net result is this. So this is sum of complex numbers. And in some situations, you can add a lot of complex numbers that come back to the origin, and the net result is 0. So again, we see that visualizing complex numbers graphically in complex plane is a useful tool. Keep that in mind. It might come handy at some point. That's all I wanted to add. Thanks.